So I'm going to talk about dihybrid crosses and chi-square tests. So in corn, purple coloration is dominant to yellow coloration, and there are also different texture phenotypes. So smooth texture is dominant to a shrunken texture. So in total, we have 4 different grain types. You can either have purple and smooth kernels, purple and shrunken, yellow and smooth, or yellow and shrunken kernels. So note the difference between the dominant alleles and the recessive alleles. The dominant alleles are going to likely be more numerous than the recessive alleles. That's not necessarily always the case, but dominant alleles are expressed in the presence of a recessive allele. So the only way recessive alleles are going to be expressed is if you have 2 recessive alleles for that trait. So let's take a look at what happens with a dihybrid cross where we have 2 parents, 2 heterozygotes that are heterozygous for these different types of alleles, the coloration and the texture alleles. So a dihybrid Punnett square can allow us to determine the probability of inheriting certain genes. So with a Punnett square like this, we can predict what the genotypes would be like in the offspring. So there are 16 boxes total, and you can see when we cross 2 heterozygous parents, we get 9 boxes that are purple and smooth, 3 boxes are purple and shrunken, 3 are yellow and smooth, and 1 is yellow and shrunken. So this gives us a phenotypic ratio of 9 to 3 to 3 to 1. So keep in mind, out of these 16 boxes, 9 out of 16 represents a 9 out of 16 chance that the offspring will be purple and smooth. There's a 3 out of 16 chance that the offspring could be purple and shrunken or yellow and smooth, and a 1 out of 16 chance that offspring are yellow and shrunken. So if we have an ear of corn that is produced by a dihybrid cross of 2 heterozygotes, we can examine what the actual offspring are. So the Punnett square allows us to predict the probabilities of the genotypes. Now we are looking at what the actual number of different phenotypes and genotypes is. So the resulting ear of corn has 381 grains, so basically 381 offspring. And we have observed that 216 are purple and smooth, we have 79 that are purple and shrunken, and so on and so forth. So you can see this table here. And our question is to basically test the hypothesis that our data reflects what we predict with a dihybrid cross. That should give us an expected phenotype ratio of 9 to 3 to 3 to 1. So that's basically the theoretical expectation. Does the reality fit that expectation? That's what we are going to find out. So we have to fill out this table. So to determine the observed ratio, we divide the number of each phenotype by the phenotype with the lowest number of grains. So we would take 216 and divide that by 21, because the yellow and shrunken phenotype occurs the least often here. So we will do this for all of the boxes in the observed ratio table. Then we need to put in our expected ratio. So this is our 9 to 3 to 3 to 1 theoretical ratio. So take a look at how the observed ratio compares with the expected ratio. They are somewhat close. They're not exactly the same, but they are within the ballpark. So we might not be too far off, or at least our observations of this ear of corn might match pretty closely with what the expected ratio is. To determine the expected number, we need to multiply the total grain number by the expected ratio for this cross. So remember previously with the Punnett square table, we have 16 boxes in that Punnett square table, and 9 out of 16 represented the purple and smooth alleles and whatnot. So we need to multiply our total grain number by these fractions. So we would multiply 381, which is our total, times 9/16, and this will give us 214. And we continue down to fill out the chart. And this basically means that we would expect to have 214 purple smooth kernels in our ear of corn. And our actual observation was 216, so it was very close to what we would expect. So now we need to do the chi-square test. And we have a formula for the chi-square. And it looks a bit complex, but you're basically just subtracting the observed number, or the expected number from the observed number, squaring it, and then dividing it by the expected number. So we would take, for our purple and smooth phenotype, the observed number, which is 216 kernels, subtract our expected number, which was 214. So that gives us 2. Then we would square it. 2 squared gives us 4. And then we would divide 4 by the expected number. And that gives us 0.019. And we do that for the rest of the phenotypes. Then the next thing we would do is add up all 4 values in the chi-square column. And this will give us a chi-square value. So we will have to look at a chi-square table and see where our chi-square value fits within that table. So this will give us a probability value. And remember, we've talked about p-values before. And if you have a p-value of something that's less than 0.05, it's statistically significant and whatnot. So remember that for particular tests, the p-value is given to us in that kind of format. In the chi-square table, the p-value is given to us in a slightly different format. So it's giving us a percentage of the probability that our hypothesis is correct. So there's a few things we need to know. We need to figure out what the degree of freedom means. And this is basically the number of phenotypes that we have for a dihybrid cross like this, -1. So remember, we have those 4 different grain phenotypes. We would subtract 1, and this would give us a DF of 3. So for dihybrid crosses like this, the DF is going to be 3 when we have these 4 phenotypes. So what we need to do is find the 3rd row in our chi-square table, and then find the value that most closely matches our chi-square value. So we got 1.802. So we need to find the number in the 3rd row that is closest to 1.802, and that is 1.85. So then we go to the top of the column, and this gives us our p-value. And our chi-square value lines up with 0.60. So you can convert this decimal to a percentage. And this means that our hypothesis has a 60% chance of being correct. So basically, the steps you want to do is go through this table and you'll need to put in your observed ratios, your expected ratios, find what the expected number of grain phenotypes should be, and then use the chi-square test to do that. And then once you get your chi-square value, you will look it up in the table to determine your probability. So the answer to our question is that our hypothesis has a 60% chance of being correct. And you can try out this next problem here, and you're going to do the same steps that we did with the first example. So in this case, we have pea plants, and purple coloration is dominant to red coloration, and long pollen is dominant to round pollen. So follow the same steps and determine the probability of our hypothesis being supported. And once you do that, we can check what the answer is. So this is what you should have found for this problem here. We should have a 70% chance of being correct. So that's how you would do a dihybrid cross and analyze a probability value in a chi-square test.